Good morning, good afternoon, or good evening, depending upon where you are in the world, and welcome to today's webinar, Securing IoT Systems with a Root of Trust, brought to you by Tech Online, Synopsys, and broadcast by UBM. I'm Chris Keach, and I'll be your moderator today. We have just a few brief announcements before we begin. First, the slides will advance automatically throughout the event. You may also download a copy of the slides by clicking on the green folder icon located at the bottom of your screen. You can also participate in our Q&A session by asking questions at any time during this webinar. Just type your question into the Q&A text area located to the right of the presentation window, and then click the Submit button. At this time, we recommend that you disable your computer's pop-up blockers. This will allow the slides to advance automatically throughout the event. And at the end of the webinar, we will ask you to complete our feedback form. Your feedback will provide us with valuable information on how we can improve future events. And you can also launch the survey at any time by clicking on the red survey button at the bottom of your console. Please note that we'll try to answer as many questions as we can at the end of the webinar today, but if we do not get to your question today, someone will get back to you via email. And if you're experiencing any technical problems, please type your issue into the Q&A text area, and we will be glad to offer one-on-one assistance. And now on to the presentation, Securing IoT Systems with a Root of Trust. Discussing today's topic is Mike Borza. Mike has more than 20 years of leadership experience in security system and safety critical system engineering. He was founder and CTO of Elliptic Technologies, which was recently acquired by Synopsys. Mike has been an active contributor to the Security Task Group of IEEE 802.1, was an editor of the 802.1 AR Secure Device Identifier Standard, is one of the founding members of the Purple Foundation and co-chair of its Security Engineering Group, and chairs the Embassy IoT Security Benchmark Working Group. Welcome, Mike. It's with great pleasure I now turn it over to you to begin today's presentation. Mike?
Thanks very much, Chris, and welcome, everyone. Happy to have you here. Our agenda for today is basically to start with a look at some of the threats and challenges and some of the considerations that you'll have as designers of IoT devices. We'll get into a little overview of the Synopsys tRoot Root of Trust device, and then use that information to look at some of the applications for the Root of Trust in actual system implementations. So I don't think it's a surprise to anybody who's attending this webinar that security threats are increasing very rapidly in the internet and in the IoT, and that attack sophistication is increasing. We're starting to see that knowledge of proprietary networks is no longer sufficient to keep people out. The information is available widely on the internet, and so attackers can be assumed to know what the network architecture is for any particular system they happen to be looking at. Multi-stage attacks are common, and these are the kinds of attacks in which somebody uses an initial access to the system, for example, getting control of a radio controller or the CPU in a radio controller in order to attack the next features of the system that it's attached to. And then the massive interconnection of different network flavors means that vulnerabilities in any one of those network interfaces can create vulnerabilities in the entire network. Simple attacks exploiting defects that are already in the system are still the most common that we see. The number of attacks that are successfully launched just by guessing what the root password for a system is and finding that it hasn't been changed from its default configuration is kind of astounding. And there is a lack today of widely adopted standards, or there are many standards that are being proposed, but this fragmentation hinders both interoperability, and it also increases the complexity of systems that are going to implement Internet of Things protocols because of the large number of different kinds of communication protocols are going to need to deal with. And in some cases, this is being used to create walled ecosystems, but in other cases, it's just creating confusion and complexity that leads to less secure systems. So some of the industry segments that are real drivers for the hardware root of trust and for improving system security through these are things like industrial internet. These are both control networks on the manufacturing floor as well as public infrastructure networks, networks in the smart grid and things like that. Of course, automotive attacks have been well documented and quite widely reported. and they continue to be a serious concern. There is some leadership being shown there, but it's really coming a little bit slower than it should be. Entertainment continues to offer many new avenues for the IoT. So we're seeing more and more over-the-top services are being offered in different locales. And of course, places like healthcare have very strong requirements for identification and authentication. You really don't want your ex-wife reprogramming your pacemaker. And so you need to have a high level of assurance that these devices are being programmed and operated by the people who are authorized to do that. Some of the general challenges that are emerging for people developing IoT devices, I'd say that system design methodology is not really keeping up in the early IoT. We're seeing a lot of basic features that are lacking in devices. So secure boot and secure updates are not a default condition for a lot of devices, and seeing a lot of haphazard or ad hoc provisioning protocols that are being implemented that are not terribly secure. Seeing a large number of trust models for different kinds of walled garden ecosystems, but really I think the IoT is going to be really enabled and take off when you have a large number of open ecosystems that benefit from the diversity of devices and diversity of information that's being reported by them. And that's when the real interesting applications in the IoT are going to start to exist. Privacy and the right to be anonymous is now starting to clash with strong identity requirements, and there are cryptographic protocols to address each of these things, but people are becoming more concerned about their privacy even as they're gaining the benefit of strong identity protections. Unfortunately, with some of the incidents that we've seen recently, you're starting to see political policies that want to weaken cryptography. This is going to fail in many regards. For one thing, any of the bad guys will continue to use strong protocols, and they'll just wrap them in the weak protocols that are approved for general distribution. But weakening cryptography generally makes all users more vulnerable to attacks. And we're also seeing a move towards legislating standards as a kind of a response to the failure of the industry to take responsibility for its own systems. And again, that's not really going to lead to a desirable situation. I think it behooves all of us to kind of step up to the plate and make it unnecessary to create legislated solutions to what should be engineering challenges. Some of the common vulnerabilities that we see, well, with the rush of products to market, some of the security implementations are poor or completely non-existent. You have physical access to devices, and especially through things like Ethernet or UART or JTAG ports that are unprotected. The number of small devices that you can boot and replace the Bootstrap ROM using a TFTP protocol over an Ethernet port or a JTAG port during boot time is quite surprising. Unencrypted storage and external flash is still commonplace, and attackers will use that to understand the code and to look for credentials and encrypted data that they can exploit later on. We're seeing a lot of obsolete versions of critical libraries in some of the real-time Linux distributions. So libraries like OpenSSL, there are several versions out of date, and we'll have well-known vulnerabilities connected with them that are being exploited and re-exploited by attackers. You still see a fair bit of clear text communications, even for authentication protocols. Device web server interfaces are particularly vulnerable. A lot of them are implemented in script languages, and some of them, the text that's entered in text fields is not properly tested or checked, and that leads to the ability to gain control of these devices using things like shell script or shell commands through the user input entries in a device web server interface. Of course, we see lots of backdoor credentials that were installed for legitimate reasons, either for testing or debugging purposes during design and manufacturing, but those things should be turned off when the product ships, and frequently you don't find that is the case. I already mentioned that default credentials that are built into devices continue to be exploited because a lot of times people just plug the device in and start using it and never bother to change that. In a sense, that's the stupidity of users, but knowing that they're going to behave that way, it really makes some sense to find a better way to handle a lot of these kinds of provisioning problems. And I think the other thing that's really kind of key here is that we see protocols and user interfaces that are vulnerable to buffer overflow attacks as kind of a primary method of gaining firmware control of a device at runtime. And so these things need to be designed for, tested for, and eliminated from the system before it ships. So a few of the terms that we'll be discussing or using here today, we have symmetric cryptography. This really is just shared key cryptography in which the same key is used to encrypt and decrypt a piece of data. It can be used in communication protocols, or it can be used for storing data. Asymmetric cryptography is the counterpart to that. It uses a pair of keys that are in some sense a mathematical inverse of each other, so that a private key is used to encrypt a piece of data, and then the corresponding public key can be used to decrypt that data. The role of the private and public key is somewhat arbitrary, and so these are sometimes reversed depending on the particular protocol that's being used. Cryptographic hashing is the other kind of pillar of cryptographic operations, and it's used to create a fixed length identifier or representative of a piece of data using a hash function or a digest function. And that hash becomes a unique representative of that data. So the probability of finding two data objects that hash to the exact same value is extremely low, and ideally zero for a perfect cryptographic hash. These primitives are used to build up more sophisticated protocols, things like authentication, in which one uses a secret key in order to prove that data originated at a particular entity and that it is intact as it's being received. Identification is the ability to prove one's identity by demonstrating the knowledge of a piece of secret data. And signing uses the private key of a public key pair or private public key pair in order to encrypt a hash, and then the corresponding verification operation decrypts that hash and uses the same hash function to analyze the data. And if the decrypted hash matches the hash produced by examining the data, then the device, or sorry, the verification is said to be successful. What's happening today that's kind of interesting is that security is now key to ensuring reliability and safety. And this is a change over the past few years. Safety and reliability used to be considered their own topics and independent of security features. But today you really can't say that any device that's safety critical or that has a high reliability capability is behaving in that manner if it's insecure. In other words, if an attacker or malware can get onto that device and control or upset its behavior, it's not behaving in the intended fashion. And so this is really becoming a critical issue in the case of safety and high reliability systems. Now, one of the interesting things is that security design is starting to be informed by some of the techniques that have been developed to deal with safety critical and high reliability systems. So you're starting to see checked redundant systems and those kinds of things being deployed in critical applications that have high safety requirements and high security requirements. So some desirable features of IoT security. We need strong identity functions in order to be able to answer questions like, is this the service I think it is? Is this user of my service legitimate? And is this firmware that's being delivered to me trustworthy? Does it come from a known source that I trust? Of course, the execution environment itself needs to be, its integrity needs to be tested and proven in order to assure that the software that's being run is behaving in the way that's intended. Secure storage and communications are key functions of IoT devices, and this includes both privacy in the form of encryption and integrity in the form of message authentication, which is implemented typically using a keyed hash function. Revocability is kind of a critical thing that is often overlooked at this point. That's ability to eliminate devices that are compromised and prevent them from being able to join a secure network. Scalability in the IoT, of course, goes without saying. Everybody is fond of quoting their favorite number from 20 billion to 50 billion for the number of devices that will be in the Internet of Things by some date. But it goes without saying that scalability is going to be a key thing that needs to be handled gracefully by any kind of IoT system. As I said, anonymity is becoming a more important characteristic as people become concerned that their IoT devices can be used to track them, and I think over time this is going to increase in importance. The IoT will function best if its operation is decentralized. So there are lots of good reasons why you want to be able to do this. You need robustness, reliability, availability, and the ability to work around failed parts of the Internet of Things, which is really just code for a large network. Of course, control is the other element of that. It kind of goes along with revocability. You need a way for the network to protect itself from bad actors, and some of those interventions will be manual, some of them will be automatic, and it's going to be a key part of developing a trustworthy and reliable Internet of Things. So SoC designs are going to be critical to enabling this security. Devices that are powered off have their own protection requirements. It's a good idea, and I would say essential, to prevent the theft and modification of stored code while it's sitting in a powered off state. Of course, data that's in a configured device also needs to be protected. If it's not, the credentials might be recovered, or the other data that's there might be recovered to use the device in a way that is enabling an attack on the network. In some cases, people are concerned about protecting their own intellectual property that's represented by the firmware or software that's installed in the device. As devices are powered up, it's essential to have a look at the operating environment that's going to be there and the data that's stored in the device, and assure that it's not being modified since the last time the device was started. And finally, at runtime, continuous monitoring of the integrity of the system is a good idea. It's one of the ways to help protect the system and the rest of the network from attacks that are originating in the network. And of course, secure communications is kind of a key aspect of that capability. Altogether, these create a system that can be considered to be a trusted execution environment. So it's a reliable place in which to run software that's going to power the Internet of Things. Some essential security functions then. Secure Bootstrap, I've talked about a little bit. It's the ability to authenticate the runtime environment, and some root of trust key is used in order to be able to do that, to prove that the signature on the software is authentic and that the software itself is intact, hasn't had malware installed on it or anything like that. During runtime, the ability to detect and report and respond to attacks is a great one. We're starting to see IoT devices that participate in network monitoring. Of course, they test their own code integrity and they examine the integrity of other devices that are nearby. And running applications themselves need to be proven to be reliable. Secure updates, more and more as you connect things up and they stay permanently connected to the Internet, it's essential to be able to update the security of the system, and that's going to involve being able to deliver updates securely and in trusted fashion to various devices distributed around the IoT. Onboard secure storage for user and system data is a critical function of root of trust. And securing the authenticated communications with services and entities that are authorized by the users of the system is another key function of the IoT's or of the device's root of trust. And finally, we need to be able to be flexible in dealing with evolving threats that exist in the IoT. So there's not a one-size-fits-all solution in these kinds of situations. We're going to see lots of closed systems. We are seeing lots of closed systems right now. Small devices, things like wearables, have relatively limited security requirements and relatively limited capabilities to implement those. And so the solutions that they can use are quite limited by necessity, both because of power consumption reasons, cost, and also just system size. These kinds of systems will be protected by things that are similar to a trust zone kind of root of trust. Towards the higher end, you start to see a reason to embed a hardware root of trust as devices have long lifetime in the IoT, and as they perform more and more valuable functions, it becomes more and more important to provide suitable protection for the credentials and the software that are running those systems. There'll be a lot of open systems. We see that today with routers, which are based on Linux, routers and gateways, and that will continue to be the case as we develop the IoT and IoT gateways and hubs. Containerization is starting to become popular as a means to deploy new applications to gateways, and also you're starting to see containerization in the form of virtualization, which is really a more specialized kind of containerization as a means to distribute applications that live on their own and isolated from other applications within the gateway. And these kinds of requirements only increase as you move into the high end of open systems. So you'll see multiple OSs running in these devices. In places like automobiles, you're looking at reduction of the number of computers as being a driver for this, both for mass reasons and for trying to reduce the complexity and just the sheer number of devices that are existing in these vehicles. And so virtualization is being seen as a means to do that. In order to make that work securely and reliably, it's important that those kinds of virtualization systems be supported by hardware that's capable of enforcing the separation between environments. So this brings us to some discussion of hardware roots of trust. They're used to provide trusted execution environments. If you look at the example on the right, this is really an example of a tRoot kind of system that uses an entire hardware root of trust that incorporates its own security modules. It has cryptographic accelerators as options and cryptographic cores for doing things like public key acceleration. The software itself runs inside of the trusted environment and is completely isolated by hardware from the non-trusted software that runs in the host environment. The example on the left is more similar to something that you would see in the case of trust zone or other kinds of trusted execution environments based on separating memory spaces of applications from each other. And so these require less hardware, but also have correspondingly less security and less ability to enforce separation of execution environments from each other. So the last thing I would say right now about hardware root of trust is that it's one of the best ways to eliminate physical attacks from the system, or at least to reduce the possibility of them. We see lots of attacks on devices through things like the scan chain and JTAG port, or accessing debuggers that are left enabled on a device. Side channel analysis, such as power, or electromagnetic, or timing analysis attacks are becoming more common and better known. Attackers will try decapsulating chips to see if there's some common secret that's stored across a family of chips. See lots of people with access to logic analyzers and oscilloscopes now and the ability to use those. And we also see lots of techniques for glitching devices, or for trying to inject noise into their power supplies or into their I/O pins in order to put the device into an unknown state that allows the attacker to gain control of it. Similarly, you see people operating devices outside of their specified temperature range as a means to try to get control of the device by putting it into an unknown state. And code and data analysis is key to all of this. People are using any means they can in order to gain access to the code to examine it, look for weaknesses or vulnerabilities that they can exploit. So that brings us to the tRoot hardware root of trust. And some of the design considerations that we went through as we were developing this were that we were looking for an embeddable hardware root of trust, very much like an embedded security module that could go into a chip, could operate ROMless if we chose to, and that is generally the preferred way to operate this device. It provides a firmware expansion capability, but has a fixed footprint inside the chip, and that implies that we need to be able to securely share system memory with other devices that are in the chip, such as the host CPU. It has a high level of security against physical and various kinds of logical attacks. It's designed with the requirements of FIPS 140-2 certification, common criteria certification in mind, and it incorporates side channel analysis resistance. It has self-test capability as well as runtime integrity assurance, and provides secure bootstrap capabilities for other devices that are on the chip. It will withstand attacks that originate from other devices, and it provides a full set of cryptographic operators as part of the basic specification for the system. The interaction with the other subsystems in the system on chip is through a very well-defined messaging interface, one that's been well-tested and examined for its vulnerability to exploits like buffer overflow attacks. So I said that the tRoot is really an embedded security module. The idea here is that we provide a safe environment to create, store, and use secrets within the chip, and on behalf of other applications, client applications that are running in the host CPUs. So some of the features that we incorporated into its design were secure boot and secure access controls, secure INA, identification and authentication, firmware integrity assurance, secure storage for the rest of the chip, secure debug and test access control is implemented, and we have runtime protections on the system, as well as the ability to do secure in-field updates. And as kind of side benefits to this, or features that are not particularly security related, but we have the possibility of using cryptographic means to enable functionality upgrades in the field, or to turn on features of the chip that may be dormant in particular applications. So the heart of the tRoot is a 32-bit ARC-EM CPU. It's tightly coupled, has a tightly coupled SRAM that it uses for data working memory. As well, this exposes a message-based interface to a host, and it's possible for us to use different firmware loads throughout the operational life cycle, or to load different firmware configurations depending on what the device is being asked to do. This device is generally not user programmable because the demands of the programming in that environment are so severe, and generally it's trying to operate in that environment is like trying to program with a loaded gun pointed at your head. The device is always waiting to halt itself. The secure instruction controller is a key part of the system. This is what allows us to use external RAM as storage for program memory here. The program itself is encrypted and authenticated, and it's a read-only memory as far as tRoot is concerned. We're able to provide access to the external memory via the regular system bus, so this is really just a port on the system bus. The microcontroller itself runs from cache. That cache has been carefully designed, and the way it's used is designed to avoid any kind of cache timing attacks. And tampering results in a tRoot exception that reports the violation. So we're able to detect any attempt to modify the code that's running in tRoot and respond to it in an appropriate way. And as I mentioned before, it is used in the implementation of the boot time and runtime integrity verification of the code. Secure Data Controller provides read-write data access to DRAMs, and so it gives us the ability to add memory or add dynamic memory and dynamic data to the secure environment. The key management and secure key port interface provide the ability to take the device unique key, derive a family of keys from that, and then be able to use derived keys in other cryptographic modules and distribute those securely around the chip without that being exposed to software. I'll return to the key derivation story a little bit later in the presentation. A couple of the optional devices that are incorporated into tRoot include the true random number generator. This is a FIPS an SP800-90 entropy source, so an SP800-90B source, and it interfaces to an SP800-90A pseudo-random number generator. The whole system is compliant with the requirements of SP800-90C. So this is designed to be used in very high grade encryption environments. It's capable of passing validations for FIPS 140 common criteria, and it has passed a number of evaluations for various kinds of government applications. The public key accelerator provides higher performance RSA, Diffie-Hellman, and elliptic curve operations than doing those operations in pure software. It's an optional component, and so it's only used in certain configurations of tRoot. But again, the public key operations are designed to be timing and power analysis resistant. Security protocol accelerators are provided for high bandwidth communications, and so those are used with various ciphers, AES being key among them. SHA-1, SHA-2, and SHA-3 cores are all available. We have various kinds of protocol acceleration as well, so IPsec, TLS, and other common security protocols are dealt with in a very efficient way by these security protocol accelerators. They're capable of operation to excess of a gigabit per second. And finally, the host interface to the device is through a set of ports, or rather the system interface to the device is through a set of ports that are used for this purpose. The host interface is through the HPI, host port interface, and that provides the messaging interface that's used to communicate with host CPUs. That can be a multi-channel interface, so if there are multiple CPUs around the system, or even an exposed external CPU, the tRoot device can be used to communicate to those. The DID interface is the device identity interface. This is an interface to non-volatile memory storage that's on chip. normally used for the device unique key and occasionally for other cryptographic keys that are stored in that device. The entropy interface provides an external random number generator input. It's used in the case that the tRNG is not supplied as part of the tRoot configuration. And the GPIO interface is used to implement things like physical tamper detection and response capabilities, as well as it's used to implement some of the features like scan and JTAG port controls. And finally, the UART interface is provided as a general purpose I/O capability. There are specialized libraries that are used with that. We can use that for doing things like private channel authentication from an external device. So some applications that employ tRoot. Good starting application is the secure boot process. And we'll discuss that in a moment. This is a kind of a typical SoC for a modern IoT gateway. There's a proliferation of network interfaces. Often there's a switch built into these devices, multiple Ethernet interfaces. There may be multiple Wi-Fi interfaces. And normally there will be several local area or very local wireless network interfaces such as Bluetooth Low Energy, Zigbee, Z-Wave, and other kinds of protocols. Oftentimes these are multiprocessors now, and the multiprocessors may be running in a symmetric multiprocessor configuration, or they may be running asymmetrically. There's normally some internal SRAM that's used as internal storage, and very often there are several physical interfaces to things like SPI memories, eMMC, and various kinds of ports like that. Externally, there will usually be some flash that's used to store the program, and normally the flash will be copied into SRAM or DDR memory outside of the chip in order to run once it's booted. So the idea here is that the root of trust provides protection of the device unique key and the things derived from it. It provides secure storage for the rest of the chip, and it's able to be used as an identification and authentication device for various protocols that the chip will ultimately implement. Typical bandwidth and throughput on these kinds of devices these days is in the 1 to 10 gigabits per second range. So the Secure Bootstrap process I mentioned earlier starts with tRoot, or rather with a hardware boot manager that's capable of reading the external program into DDR, into RAM, and that is normally taken from flash. On copying the program, the hardware module will then release control of tRoot, and the first thing it does is scan through its program using the secure instruction controller to analyze whether or not the program is intact. If it is intact, then the program is authentic, and tRoot's code is ready to run. tRoot starts up execution of whatever program is stored in that memory. So to validate the host code, TRAM starts by moving the host application into RAM a segment at a time, or a disk block at a time, let's say. At that point, it can authenticate the code by running a cryptographic signing or verification algorithm over the code. As I mentioned, this occurs segment by segment. As each segment is validated, it's copied out to system memory and put into DDR at the appropriate location. And once the entire code has been validated, tRoot can release the host processor to start its execution. So another capability that is highly desirable in a hardware root of trust enabled system is the ability to securely control access to the debug and scan chains. In order to do this, tRoot uses a signed request that's signed by an authority that's designed just for the purpose of enabling scan chain or debugging access. The credentials themselves can include different controls that allow turning on the debugging port but not turning on the entire scan chain access, or in some cases people want to be able to use the scan chain again for post-sales returns in order to analyze what failed in the field and secure access to that scan chain. That includes access to all of the internal testable devices, can be controlled through a new credential that has been authorized by the authority responsible for enabling chain access. So the essential idea is that an authentication protocol runs through the UART, either through a back channel to an external device like a debugging pod, or possibly through the host port interface with firmware that's running on the host device in order to enable access to tRoot. Once the access to tRoot has been authorized and the credential has been checked, the JTAG controller can be re-enabled, or the scan controller can be re-enabled as appropriate to the particular level of access that's being requested. So it's a pretty straightforward way to provide very secure access to JTAG and debugging ports. Extensible secure storage is one of the ways that we use the device unique key in order to create bindings between particular applications running in tRoot and the data that they use. So typically what happens with this is that the device ID interface, which is connected to non-volatile memory, brings in its value, and then a key generation or key derivation process is used to generate a derived key from the device unique key. This derivation process actually disconnects the value that's stored from the device unique key from the value that's used as the key generating key. So that tRoot base KGK is the key generating key for the rest of the key derivation chain that's used by applications within tRoot. Each application gets its own application key, and that application key is treated as a root of trust key for the application. It then can derive multiple keys from the app KGK in order to provide different features like secure storage or secure communication, secure identity. So applications themselves can have their own storage space. That storage space is virtually unlimited. The application data can be exported and stored in any unsecured memory. Typically, AES in CCM mode or possibly GCM mode will be used for this purpose. It's largely an application decision what mode of cryptography is used to provide that kind of access to data. So just to wrap up here, the roots of trust are often used to extend two network services and allow us to connect devices that are part of a service to that remote service. So tRoot provides this capability of strongly protecting the identity of those devices that are stored in the cloud, or that are in those devices that are operating at the end nodes in the cloud, and connect them to services that are operating in data centers. The trust and authentication models that are used are varied. In local networks, the wireless protocol that is being used, such as Bluetooth or Zigbee, determines what the INA protocol is for devices. But on the internet, the most common protocol that's emerging as the likely dominant standard is TLS. This is especially useful for RESTful services that are based on a HTTP web service model. And within TLS, there are two common methods of authenticating users of a TLS service. The first one is the username password model, where a client authenticates to the server. This is really out of band to TLS, and it's just using the fact that TLS is able to negotiate a secure channel for the device. But the better model for many of these kinds of applications is going to be based on client certificate authentication, and that's especially useful for walled garden ecosystems. So this is a PKI kind of trust model, a public key infrastructure trust model, and that will form the basis of most of the commercial ecosystems. There are the opportunities to control access very tightly, strong proofs of identity of devices within the island, and strong proofs between devices that they are all part of the same PKI island. Anonymity is typically not part of existing PKI protocols, and so there will be some desire to add that as time goes forward. So what we're going to initially see is lots of islands of PKIs, multiple PKIs that support different ecosystems. These will all be disconnected from each other. However, it's possible to use transitive trust, basically the cross-signing of the root keys for different PKIs in order to join PKIs. So even though early days of the IoT are likely to be built on different walled garden ecosystems, either joining ecosystems by cross-signing their PKIs, the PKI root keys, or simply by using certificate bundles, as is done now with internet browsers, will be possible. The advantage of using cross-signing is that it allows you to move much less data around the network because you're creating effectively new roots of trust for each of the ecosystems that authorize the access of another ecosystem within your ecosystem. So transitive trust really keeps down the amount of data that needs to be stored within the applications themselves. There's one other trust model that's kind of common in the internet, and I think we're going to see some interesting applications of it if some of the challenges can be solved. So the web of trust that's used for, especially for PGP and GPG, is commonly deployed. It's an open protocol. It's inexpensive to deploy, and there are good open source implementations around. Users themselves control who they trust. So in a sense, a user is the root of trust for their own ecosystem. And the key distribution is open and web-based. There are a number of advantages. I mentioned that it's open, it's relatively light on resources, and it's completely user-controlled. At this time, some of the disadvantages that need to be overcome are that it is difficult to scale for automation, and tools don't exist today that allow the automation of delegation of trust. Also, there's not really a good model for revocation in this system. So these are some of the things that one needs to consider if deploying this, but it does offer an alternate model for deploying multiple PKIs or deploying PKI islands. So just to wrap up here today, I think we've got a situation in which the security threats are evolving rapidly, and they're going to require that aggregation nodes like hubs and gateways be able to adapt to that evolving threat capability. One of the key takeaways for me from that is that automatic over-the-air network updates, over-the-air security updates are going to be an essential feature of the system design. Embedded hardware roots of trust are especially appropriate for high bandwidth or high throughput devices that are operating in the network. They're also critical for safety-critical devices. Because of the power consumption requirements of these kinds of capabilities, there should be a fairly capable or fairly high-powered source of energy available for these, so they won't be appropriate for a lot of small battery-powered applications. For end nodes, we'll see lower security solutions that are based on firmware or firmware with very, very modest hardware as a means to provide root of trust capabilities within those small devices. tRoot has numerous functions for the system that it's been embedded into, and can be used to extend its capabilities quite handily. And I think we're going to see a lot of evolution in the trust models that are used in IoT as we head forward in time. So with that, I think I'm going to turn control back over to Chris.
All right, thank you, Mike. Great presentation. Now, before we begin with today's Q&A, please fill out the feedback form that's opened up on your computer. If your pop-up blockers have prevented the form from launching on your computer, you can click on the red survey icon at the bottom of your screen. And to complete the form, please press the Submit Answer button at the bottom of the page. Thank you in advance for filling out the feedback form. Your participation in this survey allows us to better serve you. We're now going to move on to the question and answer portion of our event. As a reminder, to participate in our Q&A session, just type your question into the text box located to the right of the presentation window, or click on the Q&A icon at the bottom of your screen, and then click the Submit button. And with that, we're going to go ahead and get started with our first question. Just as a reminder to our audience, though, if we don't get to your question today, someone will get back to you via email. So let's take a look now at our first question. Our first question looks like, what is TEE, Mike?
Well, TEE is short for Trusted Execution Environment. This is really a general term that means an environment in which the software that's executing and the hardware that it's executing on can be trusted. And so tRoot is one way to provide a T, but there are also other ways to provide the same kind of capability. Essentially, though, it's just the idea that there's a safe location to execute firmware that has proven its reliability or its ability to run a certain amount of firmware on behalf of other applications in the system.
All right, Mike, our next question for you. Do you have any recommendations of security guidelines or frameworks for the Internet of Things?
Well, the closest thing to a framework that we're seeing right now is RESTful web applications built around or on top of TLS. But in terms of general purpose framework, I haven't really seen a good one yet. I think we're seeing several emerge, but none of them is really standardized yet.
All right, Mike, our next one for you. Can you please compare tRoot to TPM?
That's a good question. tRoot is similar in a lot of ways to TPM, and it provides a lot of the same capabilities as a trusted platform module. As it exists today, tRoot doesn't implement the Trusted Computing Group's TPM functions. So the TPM has a predefined user interface or a predefined system interface with a messaging protocol that has very tight standards. And so tRoot is less formalized than TPM. But in terms of capabilities, it provides a lot of the same capabilities. And in terms of its ability to execute functions securely, it provides a lot of the same capabilities. I think the one other thing that is a major difference between a TPM and tRoot is that tRoot is embedded right in the chip, and so it doesn't have to expose any of its communications over system buses that are external to the chip, whereas a TPM today is an external chip. I think you will see some movement towards more and more TPM-like functionality in tRoot and similar kinds of embedded devices.
All right, Mike, our next one for you. Please clarify the role of the optional PKA on tRoot.
Sure. The optional PKA is used to provide accelerated functions for RSA, for Diffie-Hellman, for elliptic curve cryptography. As a public key accelerator, it actually performs large math operations more efficiently than the CPU does. So the most simple configuration of tRoot uses firmware running on the ARC-EM CPU to perform those asymmetric cryptography operations. The public key accelerator provides modular exponentiation capabilities. It provides point add, point multiply, and those kinds of functions and then works with firmware that's actually running on the RTM to implement the cryptographic algorithms that are being called up. And so it's an accelerator. It does provide power analysis resistance capability and timing analysis resistance capabilities, but it's an accelerator to make the operations go faster, and that's its predominant function.
All right, Mike, we have time for probably just one more, maybe two. This one says, can I swap out the CPU for my own CPU in tRoot? And if so, how do I know the security measures are still working?
Well, the short answer is no, you can't. We thought about that, and in order to provide the security assurances that people are looking for with tRoot, the processor was basically chosen and has been hardened into tRoot so that we can provide that protection.
All right, and we'll sneak one more in here. Is there a common software interface proposed to interface with the new HW root of trust?
There's no single standard yet. Global Platform does provide some standards for these, and so it's possible to implement the Global Platform standards, and we're looking at that as one of the avenues for this. The other logical standard would be something like PKCS11, and so it would essentially create what looks like a smart card interface to a tRoot kind of device. Not all of the capabilities would be available through PKCS11. The one other one that we've been asked about from time to time has been the TPM Trusted Software Stack, and the issue with that is that it's a very large stack of software that's involved in that, and so we don't necessarily want to be taking up that much space in a relatively small device.
All right, Mike. Well, that looks like all the time that we have for questions for today. Thank you for a great Q&A session and a great presentation. And for more information related to today's webinar, please visit any of the resource links available in the green folder icon at the bottom of your screen. Within the next 24 hours, you'll receive a personalized follow-up email with details and a link to today's presentation on demand. And once again, if we did not get to your question today, someone will get back to you via email. Thank you again for attending today's webinar, Securing IoT Systems with a Root of Trust, brought to you by Tech Online and Synopsys. This webinar is copyright 2016 by UBM. The presentation materials are owned by or copyrighted by Tech Online and Synopsys, and the individual speaker is solely responsible for his content and opinions. On behalf of our guests, Synopsys, and Mike Borza, I'm Chris Keach. We'd like to thank you for your time, and we hope you have a great day.